Welcome back to the finale of our meeting. Our speaker for this session is Professor Ashoke Sen. Professor Ashoke Sen is Infosys Madhava Chair Professor at ICTS Bangalore. Formerly, he was also a distinguished professor at the Harish Chandra Research Institute in Prayagraj. He works on string theory, a framework for the study of quantum gravity and the fundamental laws of nature. He has made pivotal contributions to the study of duality symmetry in string theory and field theory, the interpretation of instabilities in the landscape of string theory, and the precise accounting for black hole entropy. His honors include ICTP Prize, SS Bhatnagar Award, TWAS Prize, Padma Shri, Pius 9 Gold Medal, Infosys Prize in Mathematical Sciences, the Breakthrough Prize in Fundamental Physics, Padma Bhushan, and Dirac Medal. He is an elected Fellow of the Royal Society London, Third World Academy of Sciences, and all three academies in India, National Academy of Sciences, India, Indian National Science Academy, and Indian Academy of Sciences. We are very happy to have you here, and he will be telling us about why Siegel modular forms are relevant for black hole physics. Over to you.
Okay, thank you very much. And I would like to thank the organizers for inviting me here and giving me this opportunity to speak. So my talk is on the connection between Siegel modular forms and black holes. So I thought I'll take this opportunity to, the first few slides, I'll try to introduce the problem with black holes. Okay. And this is probably the most difficult part of the communication process. So what I have done is that I have prepared one slide, okay, which translates the language from physics to mathematics, at least for the first few slides. It's not a universal translation, okay, and that's what I'll start with, at the risk of getting beaten up by my physicist friends. So here it is. Okay. So in the next few slides, what I'll mean by theory is a set of differential equations. Okay. Black hole will be a solution to these equations. Okay. I'll talk about the mass and charge carried by the black hole. Okay. Those you can think of as integration constants that appear while finding the solution to these differential equations. Okay. Entropy, which is a function of mass and the charges, will be a number that is computed from the solution. Temperature is another number that we compute from the solution. And then supersymmetric theory will correspond to a special class of theories, okay, and hence a special set of differential equations. Extremal black hole will correspond to a special choice of the integration constants. Okay. And the special choice refers to the choice which sets the temperature to 0. Okay. So this is one condition among these parameters, and this determines the mass in terms of the charges. Okay. And so the entropy becomes only a function of the charge. So with this, let me give an introduction to black holes, okay, and then I'll come to Siegel modular form. So we consider a theory of gravity possibly coupled to other fields like electromagnetic fields. So here black holes are classical solutions to the equations of motion. Okay, and this is perhaps the most famous of those equations, the Einstein's equations, which determine the metric of space-time. Here R mu nu is the Ricci tensor, this is the curvature scalar, and this is the metric of space-time. And then there are various other equations which determine the other fields. We'll be considering simplest kind of black holes, which are spherically symmetric. And one key feature of black hole solutions are that they are surrounded by a spherical surface. This is a really hypothetical surface. There is nothing special on that surface. Nevertheless, it acts as a one-way membrane, okay, by curving the space-time in such a way that you can go from outside to inside, but you cannot come out. Okay, coming out of a black hole will be as difficult as traveling backwards in time. Now, in quantum theory, the black hole behaves as a thermal object which carries temperature, entropy, etc. Okay, think of a hot gas in a box. Okay, that's the kind of behavior the black hole has. Okay. And in particular, the entropy of the black hole, okay, is given by a very simple formula which is written here. Okay. So the only non-universal part of this is the area term. Right? So A is the area of the horizon that you saw here. And the rest are all universal constants. C, for example, is the speed of light in the vacuum. G is the Newton's gravitational constant, which measures the gravitational force between two objects. H bar is the Planck's constant, okay, which appears in quantum mechanics. And as you can see, as I already said, other than A, all other quantities in this formula are universal constants of nature. I should also add that this formula is correct when the black hole is very big, okay, which means that when the area is big. Okay. But when that is not the case, there are corrections to this formula which could involve logarithm of A or 1 over A, 1 over A square, and so on. So you should really think of this as a first term in a power series expansion in inverse size of the black hole. Now, the area in turn is determined from the mass and charges that the black hole carry. Okay, as I said, these are the integration constants that you use for getting the solution. Okay. And so this gives a relation between the entropy and the mass and the charge. Okay, because area you can compute in terms of the entropy, you have a formula in terms of the area, but that in turn is determined in terms of the mass and the charges. Okay. And I should also say here that Q should really be regarded as a collection of several numbers, and this depends on what particular kind of theory you are considering. Okay. And these label different types of charges that the black hole can carry. And here is a central question that we would like to answer in black hole physics. Okay. That in statistical physics, when you have a box of gas, for example, okay, where you apply thermodynamics, the entropy of a system has an interpretation as a result of a counting problem. In particular, e to the s counts the dimension of the Hilbert space of the system. Okay, this I'll make more precise later. Okay, it's a Hilbert space with some qualification. But this leads to the question that does the entropy of the black hole, okay, which is e to the s, okay, also have a similar interpretation? Does it count the dimension of some Hilbert space? Now, it turns out that in order to make this question precise, we need to refine this a bit. The first reason that we need a refinement is that if you consider a generic black hole, that, as we have already seen, has temperature, and as a result, it radiates away its energy. Okay, just like any hot object radiates away its energy, the black hole is no exception. So it's really a time-dependent system. And because it's a time-dependent system, the Hilbert space of such a system will also evolve with time due to interaction with the environment. Okay. So again, imagine a box of gas, okay, which is kept in isolation, that has a fixed Hilbert space. But now imagine that it's allowed to interact with the environment. Maybe there's a small hole in the box. Okay. Some of the gas molecules may leak out, some of the gas molecules can come in from outside. Okay. And as a result, the actual system changes with time. Okay. So the dimension of the Hilbert space of the system also evolves with time. Okay. So a finite temperature black hole is a time-dependent system. Okay. And so we avoid this. Okay, this is the simplest case. Of course, eventually we'd like to do better. But we can avoid this by considering an extremal black hole in a supersymmetric theory, which as we have already discussed, by definition has zero temperature. So for this, the mass is fixed, there is no radiation. So it's fixed in terms of the charges. So the entropy now becomes a function of the charges alone. Okay, which you just substitute for m as to whatever function is required to make the temperature zero. Okay, the second reason that we have to go beyond, we have to do even more specialization is the following. Okay. So as I said, we will be considering supersymmetric theories. Okay. So these theories turn out to have moduli spaces, okay, which means that we don't have a single theory, we have a set of parameters that label the theory. Now, there are two particular regions in this moduli space, okay, one which we'll call the weak coupling region, and the other one we'll call the black hole region. In these two regions, the total Hilbert space of the theory factorizes. So here I have denoted it pictorially by thinking of moduli space as one-dimensional. In general, it's a multidimensional object. Okay. But nevertheless, in some region of the moduli space, okay, the total Hilbert space, that means black hole plus the whole environment, factorizes. Okay. In another regime, okay, which is called the black hole regime. Here again, the total Hilbert space factorizes. Okay. But in between, okay, there is no factorization. Okay, everything is mixed. You cannot identify the Hilbert space as a product of two separate vector spaces. So because of this, okay, in general, what I'm calling H prime BH here, the black hole Hilbert space, this is not really the same as this one, okay, because in between you cannot continue from here to here. Okay. So dimension of H prime BH can differ from dimension of HBH. Okay. I'll explain in the next slide why this is important. The reason that it's important is because with our current technology, we can calculate this. Okay, in fact, we can calculate this because in this weak coupling region, not only that there is a single split like this, the whole Hilbert space becomes a product of harmonic oscillators, okay, which I'll explain later. And hence, it's easy to count the dimension of H prime BH. But the black hole description is valid here. So what we want to do is we want to compare e to the FQ, the entropy, with the dimension of HBH, because that's what the Hilbert space of the black hole is. So you cannot directly compare something that you can calculate from the black hole side, okay, with something that you can count, which is the dimension of this. Okay. And so this requires doing a little more trick. So the remedy turns out to be study what is called the index. So I have denoted the index here. Okay, so let me explain this. Okay. So the definition of the index doesn't require splitting the Hilbert space. Okay, we now take the trace over the total Hilbert space. Okay, where there is of course no confusion. You don't care about what is black hole, what is the environment. You in this total Hilbert space, you fix the total charge. Okay, that's what it means by trace H total Q. You fix the total charge. Okay, so you count only those states which carry a particular charge. Okay. And then you take the trace of a Z2 transformation sigma. Okay, so sigma essentially takes 1 for bosonic states and -1 for fermionic states. Okay. Now, if this language of bosons and fermions are not familiar, okay, you can just think of this Hilbert space as being having a Z2 grading. Okay. And sigma is basically the generator of that Z2 transformation. Okay, so you count states with signs. Okay. You count with 1 if sigma is 1, if you count with -1 if sigma is -1. So this is close to the dimension of the Hilbert space, but not quite, right? If sigma had been 1, then this would have counted the total dimension of the Hilbert space with a given charge. Now, the reason that this is useful is because one can show, first of all, that this quantity is independent of the moduli. Okay, so with this, when you calculate weak coupling or the black hole region, gives the same result. Okay, there is a general theorem of that kind. Okay, there is some modification of this which I'll discuss later. Okay, but for now we can assume that this is independent of the moduli. This can be computed at weak coupling. Okay, because as I said, at weak coupling you can in fact count anything, right? Because it becomes a product of Hilbert space of harmonic oscillators. And furthermore, in the black hole regime, one can argue that up to computable corrections, again which I'll discuss later, this quantity can get contribution only from states in HBH. Okay, so it gets contribution only from this part of the total Hilbert space. This part doesn't contribute. Finally, one can show that each state in HBH have sigma equal to 1. They are all bosonic states. So when you calculate IQ, okay, from the black hole side, in the black hole regime, you get trace HBHQ of 1. You could replace H total by HBH because that's what contributes. You replace sigma by 1 because all states have sigma equal to 1. So that becomes a dimension of HBH of a fixed charge Q, and that is supposed to be e to the f of Q because that's the exponential of the entropy. So now we have two things that we can compare. Right? We have FQ on one side, which you can calculate via geometry, the area of the event horizon and corrections. And we have this on the other side, IQ, okay, which you can count from in the weak coupling side. Okay, and there you have some counting problem. Okay, and the question we'd ask is, are these two the same? Yes.
Can you point that only sigma equal to 1?
Yeah, so I'll not be able to elaborate in detail, but basically what you can show is that the black hole horizon, right, is forced to be spherically symmetric by supersymmetry. Okay. Hence, average angular momentum is 0. Okay. Furthermore, we can argue that the near horizon geometry describes a microcanonical ensemble. So all states have the same angular momentum. Okay. So if the average angular momentum is 0, then all states have angular momentum 0, right? And that means all states are bosonic. Okay. That's the reason why sigma is forced to be 1 for these. Okay, so here again I have stated the problem. Okay, I have already said what I have said earlier. So is f of q equal to log of iq? And let me remind you that f of q is calculated from the geometry of the black hole spacetime, right, which is of this form, this plus corrections. I of q is computed from the counting of states. And this is where the Siegel modular form enters. It turns out that the Siegel modular forms, that for at least for a class of string theories known as n equal to 4 supersymmetric theories, Siegel modular forms enter in the computation of IQ. So what I'll do is that I'll first explain the results and then outline the derivation. So this is more or less the introductory part. Are there any questions at this point? So if not, I'll go ahead and explain how IQ is related to Siegel modular forms. So in the n equal to 4 supersymmetric string theories, it turns out that you have a large group of duality symmetries. Okay. There are a lot of charges, okay, but there is a symmetry that relates many of these charges to each other, right? IQ for one charge can be related to IQ for a different charge, okay, by using this symmetry. Okay. And so effectively you can focus on a system that carries only 3 independent charges, okay, which I have called Q1, Q2 and Q3. Okay. And the idea is that if we know I as a function of these 3 charges, you know I for all other charges by using this duality symmetry. Another thing I didn't say earlier, but let me say it now, is that when you think of these as parameters that appear as in solutions to differential equations, okay, these are continuous parameters. Okay, but once you go into quantum theory, okay, it turns out that these take value on a lattice, so they become discrete integers. Okay, and this now leads to defining a generating function for the index, okay, which I have defined here. Okay. Rho, sigma, and nu I'll think of as 3 complex variables. Okay. And I define this generating function as simply sum over all charges, okay, with this exponent weighted by I, Q1, Q2, Q3. Okay. This is exactly a generalization of the partition function that we have been seeing in many of these lectures. And the result is that this quantity is given by the inverse of a monomorphic Siegel modular. Okay, and I'll explain what it means. So first, I'll try to give a definition of Siegel modular forms because it may be something that is not familiar to everybody. Okay, but it will be a very practical definition. I'll not go into deep mathematics behind this. Okay. So first, let me define the sp2z group. Okay. So this is a group of 4 by 4 matrices, okay, which I'll write as A, B, C, D, where these are 2 by 2 matrices. Okay. They have integer entries and they satisfy relations of this kind. Okay. Now you can see that this is a generalization of SL2z, right? If these are 1 by 1 matrices, right, then this is AD minus BC equal to 1. I is the 2 by 2 identity matrix. Okay, so if these are 1 by 1 matrices, then it will be AD minus BC equal to 1. And these will be trivial relations, right? Because these will be numbers, right? So clearly they are the same. Now what we need is not sp2z, but a subgroup of sp2z. Okay? And this subgroup will be labeled by an integer n, okay, which will take values 1, 2, 3, 5, and 7, okay, all prime numbers. Okay? We'll define Gn as a subgroup of sp2z, okay, as a group generated by 3 sets of matrices, okay, which I have written here. So it's basically G1, you consider the group generated by G1, G2, and G3, and then conjugate that group by this G0. Okay. So G0 is defined here, G1 is defined here. Okay. G3 and G2 are families of matrices, right? G3, for example, is a matrix of this kind for arbitrary lambda and mu, which are integers. And G2 is a matrix of this kind, okay, where A, B, C, D, this defines an SL2Z matrix, but there are also these congruence conditions. Okay, so this A, B, C, D in this language is really an element of gamma 1n. And one can show that if we take n equal to 1, then this G1 becomes the sp2z group, right? So sp2z is included in this set as G1, right? But other groups are subgroups. Okay, so now let me define the Siegel modular forms. So a Siegel modular form, okay, we'll be considering monomorphic Siegel modular forms. Okay. So this is a monomorphic Siegel modular form of weight k of Gn, okay, if the following conditions are satisfied. So first, it's a monomorphic function in the Siegel upper half plane. Okay, so Siegel upper half plane is defined here. So I'll use a notation that rho 2 sigma 2 and nu 2 will be the imaginary parts of rho sigma and nu, and rho 1 sigma 1 nu 1 will be the real parts of rho sigma and nu. Okay. And Siegel upper half plane requires that we impose the condition that rho 2 is positive, sigma 2 is positive, and this combination is also positive. So phi k is a monomorphic function of rho sigma and v in this subspace. Second condition, let's define a 2 by 2 matrix, 2 by 2 complex matrix, as in here. Okay, here it's a symmetric 2 by 2 complex matrix, rho nu sigma. Then if we change rho sigma and nu to rho prime sigma prime and nu prime by this transformation, a omega plus b, c omega plus d inverse with a, b, c, d in Gn, then one can first of all show that this new matrix is also symmetric. So you can read out rho prime, nu prime, and sigma prime from this new matrix. If phi k satisfies an equation of this kind, then we will call this a Siegel modular form of weight k of Gn. Okay, that's the definition of a Siegel modular form. Now, we need, okay, so this is just a mathematical part, right? What is the definition of a Siegel modular form? And what is a group Gn? Yes, indeed. Yeah, they are coming from the divisors of 24 because this is an integer for these primes. Why does 24 come? Well, in some sense, you can think of this as eta to the 24, right? That's the natural object which counts, which is a modular form, right? So I mean, if you trace it, it basically originates there. Yeah. Okay, so now, so this is the maths part. So let me now say what is the connection to physics. Okay. So as I said, we are considering a special class of theories which are n equal to 4 supersymmetric string theories, and we'll be considering even a special subset of those, right, which are called the CHL models. And these CHL models are labeled by a prime number which can take values 1, 2, 3, 5, and 7. For these theories, this generating function of IQ that I described before is given by the inverse of a Siegel modular form, and this is a precise relation, where k is related to n by this relation over here. Now notice that I have not said so far, okay, what exactly phi k is, right? This gives a general definition of Siegel modular form, okay? But which particular Siegel modular form appears in the generating function? Okay, so I'm going to give this in a special case in the next slide, but for all cases, this is known. Are there questions? Right? Okay, so we'll consider the simplest example where I'll explicitly give the Siegel modular form that appears. Okay, and that's known as the IISER cusp form. Okay, this corresponds to the case n equal to 1, and for n equal to 1, you consider this corresponds to k equal to 10. Okay, so it's a weight 10 modular form. So the way it is defined, okay, at least this is one way you can define it. Then we first define this function f of z and tau, okay, which is given here. This theta 1, the theta 2, theta 3, and theta 4 are the standard Jacobi theta functions. Now this is a weak Jacobi form. Okay, so it has an expansion of this kind. So even though this appears as an independent function of z and tau, the actual dependence on tau and z are related, so that when we expand in a Fourier expansion, okay, the coefficients are functions of 4n minus b square, where b is the coefficient of z and n is the coefficient of tau. Okay. So these coefficients are completely defined by the expansion of this function. And in terms of these coefficients, we can give what phi 10 is. Okay. And this has this product form. Okay. This is what we have for phi 10. It's a completely explicit expression. Okay. And then it requires some work to show that it actually transforms as a modular form of sp2z. And similar explicit expressions exist for all the other phi keys that are needed. Okay, the phi 2, phi 3, phi 5, and phi 7. Okay. Now let me give an outline of the derivation. Okay, I'll certainly not be able to give the full derivation, but let me just say how we arrive at this formula. Okay, and that basically comes from counting. Okay. Now, as I said, in the weak coupling regime, okay, this Hilbert space, the weak coupling Hilbert space, basically becomes the product of many bosonic and fermionic harmonic oscillators. Okay. So let me explain what a bosonic harmonic oscillator is. Okay. So a bosonic harmonic oscillator basically is a system where the Hilbert space states are labeled by a single non-negative integer n, and the nth state carries charge, which is a multiple n times a fixed set of numbers, nq1, nq2, nq3. Okay. You can also think of this as if this Hilbert space is built from particles. Okay. N, the state labeled by n corresponds to n particles. Right? So imagine that each particle carries charge q1, q2, q3. Okay. So 0 particles will carry no charge. Right? That's n equal to 0 state. 1 particle will carry charge q1, q2, q3. 2 particle will carry q2, q1, 2 q2, t q3, and so on. Right? That's the way we build the Hilbert space of bosonic harmonic oscillator. And because these are bosonic, all states have sigma equal to 1. So now you can easily construct the generating function. Right? You just sum over n from 0 to infinity, and this is what you get. Harmonic oscillators are similar. Okay, again, you can think of this as building states from 0 particle, 1 particle, and so on. Okay. But there are two differences from the bosonic harmonic oscillator. Okay. First, the fermions obey something called the exclusion principle. So you cannot put more than one fermion in the system. Okay. So you can have either 0 fermion state or 1 fermion state, but not 2 fermion states. So n runs from 0 and 1. The second difference is that the fermions carry sigma equal to -1. So every time you add a fermion, you put a -1 for sigma. Right? So 0 fermion state has sigma equal to 1, but 1 fermion state will have sigma equal to -1. So that's this. So generating function is given by this sum over here, and that's given here. So now we collect the result from all the oscillators. Okay. So it is a collection of many oscillators, some bosonic, some fermionic. Okay. So you label the oscillators by the index alpha with the charges q1 alpha, q2 alpha, q3 alpha. Okay. And we also define sigma alpha to be 1 for bosonic oscillators and -1 for fermionic oscillators. Okay. Then the total partition function is just given by the product of individual partition functions, right? Because they are really independent systems. Okay. So here is the product. Okay. And then you have some p-factor over here. Okay. This is very much like this q to the 1 over 24 in the expression for eta. Okay. So that the physical origin of this is that these are the charges that are carried by the state even when all the oscillators have n alpha equal to 0. That means even in the absence of that 0 particle state, suppose you have no particle in any oscillator, even then the system carries some charge, and that's these. And similarly, sigma naught is plus or minus 1 depending on whether the state with all n alpha equal to 0 is a boson or a fermion. So what you do is that you collect all the oscillators, take the product, okay, which is this expression, and then you find that magically, okay, this product becomes the inverse of a Siegel modular form, okay, and precisely the kind of Siegel modular forms that I described earlier. So now we come back to the original problem. Right? We have to compare f of q and log of iq. Now iq is known exactly. When I say it's known exactly, what I mean is that if somebody gives me a Q1, Q2, Q3 value, right, I can just expand this product and read out the corresponding coefficient. Right? It's a simple program in Mathematica that you can put, that you give the Q1, Q2, Q3, and the program will tell you what the coefficient will be in this expansion. But that's not what we need for this comparison, because f of q is known in terms of an asymptotic expansion, right? Large q. So leading term in f of q, in fact, one can calculate the area, and it turns out to be of this form: pi times 4 q1, q2 minus q3 square. So how do we compare this asymptotic behavior of f of q with iq? So for this, we need to study the asymptotic expansion of iq for large charges. So here is the expression again. So what we do is that we invert this and write the I as a Fourier integral, okay, because this is a Fourier expansion. Okay, here you can also see that the lattice that in which the q1, q2, and q3 belong. q1 and q3 are integers, q2 is integer by n. Okay. So you can invert this and write I as an integral, okay, over the real parts. Okay. But this has poles, okay, and so you have to specify the integration contour. Okay, how do you decide which integration contour you should choose to carry out this integral? Okay. And for this, what you have to do is you have to go back to the generating function, okay, see where the generating function converges. Okay. And this I'll elaborate later in some more detail. So you have to go back to the generating function, see where it converges, and choose the integration contour in the region where the generating function converges. And by examining these, one finds that for most oscillators, the convergence of the left-hand side is ensured by taking the rho sigma and v, rho sigma and nu in the Siegel upper half plane. Okay. But just to make sure that individual terms are close to 1, so that the product doesn't diverge, you have to take large rho 2 sigma 2 and this condition. This is, of course, the condition for the Siegel upper half plane. So we start with this integral, okay, and I choose the contour at fixed imaginary parts, because these integrals are over the real parts of rho sigma and v. So imaginary parts we fix, and we fix it at large rho 2 and sigma 2 and rho 2 sigma 2 minus nu 2 square positive. Now it turns out that this doesn't remove the ambiguities, right? Even in this region, large rho 2 sigma 2 nu 2, okay, as you move, keeping rho 2 sigma 2 and nu 2 large, okay, sometimes you encounter poles, okay, and then you have to specify where you take the contour. Okay. So this I'll come back a little later. Okay. Fortunately, what one finds is that these ambiguities do not affect the large Q expansion. Okay. It is true that if you move in this large rho 2 sigma 2 nu 2 space, right, sometimes you cross poles, so the result changes by the residue at the pole. Okay. But the result, that the contribution from those residues, okay, is exponentially subleading compared to e to the f of q with which you are trying to compare the result. Okay. So those residues are not going to affect this comparison of what we get from iq with what you get from f of q. Okay. So we fix some rho 2 sigma 2 nu 2 without worrying about where exactly we fix it. Okay. And then what we do is we start deforming the contour by lowering the values of rho 2 sigma 2 and nu 2, okay, with the ratios being kept fixed. Okay. And the idea is that as you lower it, right, by Cauchy's theorem, the result doesn't change till you hit a pole. Okay, so you see where you feed the first pole. Okay. And the first pole is encountered. So this is the first pole that you encountered as you are lowering the contour. Okay. So what we do is that we deform the contour through this pole, okay, and in that process we pick up residue at the pole, right? So the original integral you can now write as a new integral where the contour has gone below this pole, okay, and plus the residue at the pole. Now one can estimate the contribution from the deformed contour, okay, where the contour has gone below the location of the pole, and one can show that that contribution is exponentially small compared to the residue at the pole. So we focus on the residue contribution, right, because that gives the dominant behavior at large charges. Okay. This becomes a two-dimensional integral because you see you have three integrals, rho 1, sigma 1 and nu 1. nu 1 integral you do by the Cauchy's theorem. Okay, so now you are left with two integrals, rho 1 and sigma 1. Okay. And this integral, okay, is amenable to evaluation using the steepest descent method, okay, or what is also more generally called the left-hand symbol. Okay. And this leads to this result over here, as you can see, okay, which is exactly f of q that we saw earlier, right? So f of q was calculated by calculating the area of the event horizon. This is calculated by simply studying the asymptotic behavior of I of q. So indeed, we see that the leading term in this agrees with the area contribution to the entropy. Other questions? Yes. That sum? Yes. I'll come to that. I'll come to the subdominant terms. Right? So the full answer is ambiguous, right? Because the subdominant terms are different depending on where you choose the contour. Right? So I'll describe later how to choose the contour, right? If you want to keep track of the subdominant terms. Okay, but once you have gotten the answer, right? Once you have done so much work, you shouldn't stop here. Right? So you should go into the subdominant terms, right? So now these are not exponentially subdominant, right? These are power subdominant in the entropy. So what about these terms? So these terms, for IQ, in fact, these terms are relatively straightforward to compute because you have a two-dimensional integral, right? And you have a saddle point. So you are just evaluating the integral using the steepest descent contour. So you can, in fact, go to any order that you like, right, with little work because you have a saddle point method. So in IQ, finding these dots are relatively simple, but the subleading correction to the black hole entropy are much more difficult to compute. Okay, because that requires a lot more work, okay, involving string theory. But it has been done. So far, the comparison has been done up to first subleading term. Okay, and I'll give an example of this, how this comparison goes. First subleading term. Okay. So this is in the n equal to 1 case. The first subleading term in log I in the n equal to 1 case, okay, is given by this, okay, where eta is the Dedekind theta, okay, and tau is a combination of the charges. Okay, and you can see that this is positive, so tau actually lies in the upper half plane, and Dedekind theta is well defined. Okay. This is also a modular invariant combination. Okay, and this modular symmetry that you see here is essentially what we call the S duality in string theory. Okay. And the point is that this result actually agrees with f of q that is computed from black hole geometry. Okay, even though it looks pretty complicated, okay, because in the counting formula itself you have a Dedekind theta in the asymptotic expansion. Okay. And for n larger than 1, we get more complicated functions. There are more complicated modular forms of gamma 1n, okay, but every time the results agree. What you calculate from the black hole side and what you calculate from the microscopic side agrees. Okay, so now I come to the question that I left open, okay, which is the ambiguities that appear in the choice of contour. Okay, how to choose the initial contour. Okay. So you have ρ2 sigma to large, okay, and this condition, right, this is satisfied. Okay. The point is that even in this region there are poles, okay, and those poles, the poles which actually reach the region of large ρ2 and sigma 2, okay, have this linear form, is a form of a linear relation, okay, and j n1 m2, j n1 m1 and m2 are integers that have to satisfy these conditions, right? m1, for example, is n times an integer, m2 and n1 are arbitrary integers, j is an odd integer, and then there is a nonlinear relation between m1, n1, and j. So let's look at the imaginary part of this. Okay, so imaginary part is given here, okay, and the point is that whenever this vanishes, right, in the ρ2 sigma to tau 2 space, whenever this vanishes, okay, there is a chance that the contour will pass to the pole, right? Because you are setting the imaginary part to 0, the real parts are being integrated over, right? So the contour will pass to the pole. So what these lines do is to divide up the ρ2 sigma to large and ρ2 sigma to minus nu2 square positive region into many chambers that are separated by codimension 1 walls. These are the codimension 1 walls. And to visualize it, it's easiest to plot it, okay, in terms of ratio, because this condition is invariant under simultaneous scaling of rho 2, sigma 2 and nu 2. Okay, so let's look at it as a in the two-dimensional plane, okay, where this axis is nu 2 over rho 2 and this axis is sigma 2 over rho 2. Okay. And here, this is the parabola that is this condition. Okay, this is not the wall, this is really the boundary of the space. Okay. And the straight lines that you see are the various walls. Right? This one, for example, is a wall that corresponds to nu 2 equal to 0. Okay, you can see what choice of j n1 and m1 will give this. In fact, it's m1 and n1 are 0 and j is 1, right? That satisfies this condition. Okay. So there's a wall at m1 and n1 equal to 0, j equal to 1, that's this wall. Okay. Similarly, you can read out what these walls are. So this tells us that when you choose the contour, if you choose the contour here or here, the results will differ. Now, the reason that we didn't have to worry about this earlier is because the difference in IQ between neighboring chambers is determined by the residue at the pole, okay, and the residues of phi k inverse at these poles give exponentially subleading contribution related to the contribution from the pole for which we picked up the residue. Okay, in fact, these residues, if you carry out the asymptotic expansion, it turns out that it goes as exponential of root q, right, rather than exponential of root q1 q2, right, which is exponential of quadratic, exponential of square root of a quadratic expression in the charges. These residues go as exponential of a square root of a linear expression in charges. So for asymptotic expansion, it doesn't matter. Okay. Nevertheless, we need to understand the physical origin of this ambiguity, right? Because after all, we have a counting problem, right? So why is the counting problem giving this ambiguous result? Okay. Counting problems should have a definite result. It turns out that the moduli space of n equal to 4 supersymmetric string theories can also be divided up into many chambers with different IQ in different chambers. Okay. And this is what I misled you at the beginning. I said that the index is independent of where you are in the moduli space, that they don't change as you vary the moduli. Okay. It is true in each chamber separately, okay, but as you move from one chamber to next chamber, the index actually jumps. And it turns out that there is a one-to-one map between the chambers in the moduli space and the chambers in the rho 2 sigma 2 nu 2 space. And the jump in IQ between two neighboring chambers in the moduli space can be computed from the residue of phi k inverse at the corresponding pole in the rho sigma nu space. Okay. So this is a statement. Okay. But we have to now understand why is there a jump in IQ between the neighboring chambers in the moduli space. Okay. Again, we started with the counting problem. In the counting problem, we never said that it depends on where you are in the moduli space, right? So what went wrong in this counting problem that now we are finding that different chambers have different counting. So I'll give an explanation of this, okay, in both regions. Once in the weak coupling region where we actually did the counting, okay, and the other in the black hole region, okay, where we think of this as a system involving black holes. Okay, and it turns out that this has an understanding in both these regions. Okay. So let's start with the weak coupling region where we actually did the counting. What happens here is that the nature of some oscillators actually changes across the wall. Okay. So here I have given an example. Okay. Let's forget about all this counting that we did, okay, and just focus on this simple example. Okay. Imagine that we have a harmonic oscillator whose nth state is a bosonic oscillator. It's a bosonic harmonic oscillator whose nth state carries q1, q2, q3 given by 0, 0 and n plus half. Okay, this half is an overall factor that I included in the earlier case in this q1 naught, etc. Okay, but let's assume that you have q1, q2, q3 given by these. So you can calculate the generating function, which is here, right? And once you work it out, you get something like this. Case 2, the nth state of the bosonic oscillator carries q1, q2, q3 equal to 0, 0 minus n minus half. Okay, very defined spectrum, right? Calculate the generating function, okay, which is here, and you get this. And now you may see that as a function they are very close, right, with only differ by minus sign. Now imagine that you have two such oscillators. Then two such oscillators will have the same generating function but different IQ. In case 1, the actual expansion, okay, came from a sum like this, which is given here. In case 2, the expansion came from a sum like this, which is given here. So the generating functions are the same in both cases. But clearly the spectrum that you have here, right, these are all positive Q3, right, is very different from the spectrum that you have here, which is all negative Q3. So now the point is, if you want to extract the actual numbers out of this generating function, right, the difference is not in the function itself. The function is the same. But what you have to do is that if you are trying to extract the result for the first case, we have to first see where this series converge. Right? This series converges for positive nu2. Okay? So you have to take this contour for positive nu2, whereas this series converges for negative nu2. And so here, if you want to extract the numbers IQ from the partition function, you have to take the same integral, but the contour should be in the negative nu2 region. Okay? And the difference is just given by the residue at the pole. Okay, that's the way you calculate the difference between the spectrum here and the spectrum here, right? What kind of eyes you have here and what kind of eyes you have here. Are there questions? Now, in the actual problem, we have a set of oscillators of this kind, right, which changes its nature. But it's also multiplied by the contribution from the other oscillators. Okay? Nevertheless, because of this pole, right, the way you have to carry out the expansion is different in different chambers, right? That's the difference between these different oscillators. Okay? And the result for the index actually changes, right? Even though the partition function looks exactly the same as an analytic function. Okay? And we can also calculate the jump across other worlds, right? Basically, the physics is the same. Right? All you have to do is to replace nu in the previous analysis by this combination over here. So this explains why from the microscopic counting, okay, we have the same partition function, okay, nevertheless we have different I. Now explanation on the black hole side. It turns out that when you try to think of this from the black hole side, okay, we have been thinking that the black hole is one object, right, and that's what contributes to the index, right? I said there is a general result that even in the total Hilbert space, the contribution to the index comes from the black hole. That is almost true, except that there are also other systems involving black holes, okay, which are called two-centered black holes, right? Imagine that we fix the total charge, okay, but given the same total charge, okay, we can build the total charge, okay, either from a single black hole or from multiple black holes. So as long as the total charge adds up to the fixed number, so you can have two-centered black holes like this, okay, with total charge adding up to Q1, Q2, Q3. Okay. And it turns out that in the n equal to 4 supersymmetric theories, these two-centered black holes also contribute to the index. Now you may ask, what about multi-centered black holes? Why not three-centered or four-centered black holes? Okay. Those do contribute to the index, but not in these theories, right? Those contribute to the index in what is called the n equal to 2 supersymmetric theories. Okay. On the other hand, if you have more supersymmetry, like n equal to 8 supersymmetric theories, then the contribution comes only from single black hole. Okay. And so these two-centered configurations, okay, turn out to exist in some region of the moduli space, but not everywhere. Okay. So as you move in the moduli space, as you change the theory, as you change the parameters of the theory, okay, what happens is that the configuration that actually contributes to the index, that distance is fixed, okay, because you have to make sure that the electrostatic repulsion balances the gravitational attraction, right? That fixes the distance between these two black holes. Okay. But as we approach one of these worlds in the moduli space, okay, the distance between the centers start increasing, okay, and it becomes infinite distance exactly on the wall. Okay. And as you cross the wall, these states don't exist. Okay. So here, from this point of view, the jump in the index, okay, is basically captured by the particular two-centered value, the contribution to the index from the two-centered configuration that decays across the wall. Okay, so this is the understanding from the physics side, okay, from the black hole side, okay, as to why there is jump in the index. Other questions?
They are like two spherically symmetric.
Yes. Two spherically symmetric, but the whole configuration, of course, is not spherically symmetric, right? They're axially symmetric, right? Because there is an axis along which the two centered black holes lie. Pardon? At the interface, one doesn't know, because that's you're right, from a contour integral viewpoint, you're right on the pole, right? Yeah. So there you don't. From the physical viewpoint, on the wall, these are marginally bound system. Right? Their distance is going to infinity. They still exist, but it's not clear what to make of that system. Right? It's an infinite size object. So you don't try to define the index on the wall, right? But on one side of the wall, they exist as a regular two-centered system. So they do contribute to the index. On the other side of the wall, they don't exist. Right? So they don't contribute to the index. Yeah, so the fact that on the wall of marginal stability, the distance between the two goes to infinity, that follows from the solution to the differential equation, indeed. Right? So this part can be studied purely from the black hole side. If you didn't know anything about the index, right, just from the black hole side, you can study on what subspace this two-centered configuration will become infinitely separated, right? And those are the walls of marginal stability. So now we turn to the question which may be the most relevant to this conference, and that is, can we write down the generating function of the index of single-centered black holes only? That imagine that we try to take this given point in the moduli space, the index gets contribution from single-centered black holes, that's the dominant contribution, right? Most of the entropy comes from there, but there are also some subdominant contributions from two-centered black holes. Okay, there are various kinds of two-centered black holes. But we know precisely how much they contribute. Okay, one way we know, because we know how much the degeneracy jumps as you cross the wall, right? Because that's the residue at the pole. So one can ask, is it possible to subtract off the contribution from the two-centered black holes and define a generating function of the index of single-centered black holes only? So these questions are addressed to some extent by Dabholkar-Murthy Zwegers, where mock Jacobi forms played some role. But they didn't really solve the whole problem, because what they managed to do is to get a formula, but they had to use different generating function for different sets of charges. So what they did was that you have these three charges, Q1, Q2, Q3. Imagine that you keep Q1 fixed, right? Expand this in a Fourier series and keep Q1 as a fixed number. So for every Q1, you have an expansion in two variables, that they identified after subtracting the two-centered contribution as a mock Jacobi form. Even then, it fails to work in for some charges, right? Even this limited context, right? It doesn't always work. But our goal will be to write down a single generating function that captures the index of single-centered black holes for all charges. This should be possible. It's some work in progress with Ranveer and Ajit. Okay, next week we are supposed to work on this. Okay, we'll see how far we progress. Okay. And perhaps this will lead to something like mock Siegel modular form, right? We don't know, but it's some counting problem, right? And counting problems usually lead to modular forms on Siegel modular forms. So the hope is maybe this will have something to do with Siegel modular form. Okay, I see I have 4 minutes, so I have a few more things to say. So let me say it and then I'll stop. So there are other things we can do with this analysis. Okay, one is what is called the sign of the index. So we saw this is the definition of the index. Okay, this was to start with. You have the definition here. At this stage, the index can get both positive and negative contribution, right? Sigma can take plus or minus 1 value. So there is no definite reason for the index to have a fixed sign. But I said that this index gets contribution from only black hole states, and for black hole states, sigma is identically equal to 1. Right? So that's the way we say that IQ should be equal to dimension of HBH, and this, of course, is positive because it's the dimension of a Hilbert space. Right? So the fact that the black holes carry sigma equal to 1 and the fact that the contribution to the index comes purely from black holes together implies that sigma, the index will be positive. But this argument is valid only for single black holes. Right? If you have two black holes, individual black holes have sigma equal to 1. But then you have to consider the quantum mechanics that binds them, right? Because these two black holes are a system that has a quantum mechanics describing it. And that quantum mechanics can produce fermionic states. So this result that the index will be positive, it's valid for the index for single-centered black holes. You have to subtract off the ones that come from multi-centered black holes. So after extracting the single-centered black hole index from phi k, we should get positivity property of the index. So this has been checked in many cases. This has not been proven, because we don't know how to subtract the single-centered black hole in all cases. But numerically, it has been tested for a wide class of charges. For a special class of charges, this has been proved by Brinkman and Murthy. In fact, this is the special case is when one of the charges, say Q1 and Q2 are fixed, right? If you take, I think they did it for Q1 equal to 1 and Q1 equal to 2, n equal to 1 case. For those, they showed that all the indices are positive. It can be shown to be true for the asymptotic expansion. For large charges, where the multi-centered contribution is exponentially subdominant, one can check that the index is really positive. The last thing I'll say is something slightly different, which is called the twisted index. That there are subspaces of the moduli space of n equal to 4 supersymmetric theories, where the theory develops an extra ZP symmetry. And P can be 2, 3, 4, etc. There are various examples known. And so one can define what is called the twisted index, where you take the same kind of trace, except that you also insert this generator of the ZP group, G. And it turns out that this also can be counted in the weak coupling region. And this is given by Fourier expansion coefficients of a different set of Siegel modular forms. Not the ones that we started with, that counts the original index, but a different set of Siegel modular forms. And the physics from the black hole side tells us that for large charges, this index should grow as exponential of S over P. S is the original entropy divided by P. P is the order of the group. So it should go as exponential pi squared of 4q1 q2 minus q3 squared by P. And this also has been verified by studying the asymptotic growths of the twisted index computed from Siegel modular forms. The same kind of analysis that we did for the index itself, one can also do for the twisted index. One can also test the positivity property of the twisted index, and the way it goes is the following. Let's take P equal to 2, order 2 group. So we know how to calculate IQ and we know how to calculate IGQ. These are given by different Siegel modular forms. So now let's calculate half of IQ minus plus minus IGQ, right? That is given by this formula over here. And now we see that this is a projection operator, right? 1 plus minus g by 2, this projects into either g odd or g even states. And now we can use the fact that for single-centered black holes, sigma is 1, to write this as a projection operator, but now you just have the trace over the states. And this, of course, is positive, right? Because you are trying to calculate the dimension of the Hilbert space, which either are even under Z2 or odd under Z2, right? It still becomes a dimension of the Hilbert space. So this should be positive. Again, you have to remove contribution from two-centered black holes. And this has also been tested in many examples, notably in this paper. So I think that's it. I'll stop here. Thank you.
Thank you, Professor Sen. Are there any questions?
When we collect the contributions from all our later and you put in the product,
yes,
then it turned out to be magically narrow mathematical matter. What is that magic? It's from physics or math?
Well, the problem is that from the physics, we really cannot argue why there should be this GN group, right? What we can argue is that there should be a gamma 1n subgroup, which is the duality symmetric group, right, which is a very small part of this GN, right? But from physics, we don't really understand why the full GN emerges, right? And the GN is not really symmetry of IQ, because the choice of the contour, right, breaks that GN symmetry, right? Because you are taking large sigma to tau 2, right? That breaks the GN symmetry. But nevertheless, the partition function has the extra symmetry, right, which is the magic.
Any other questions? If not, let's thank Professor Sen.
Sure.
And thus we come to the conclusion of a very motivating and a very instructive meeting on harmonic mass forms, a week-long meeting. It's difficult to imagine that we just started and we are already over. So before we disperse, let's thank our two speakers, Professors Anderson and Griffin, for their instructive and inspiring lectures throughout the week. Let's also thank all the speakers of the second half who gave us very motivating talks on applications of these topics. Let's give a big hand to our two organizers for putting together an amazing meeting, and for ourselves for still being here. Now I hand over to Ajit for further remarks.
Yeah, thank you. Actually, Siddhi has made my job easier, because that was part of the things that I was going to say. Okay. Yeah, so with the last talk, we've come to the end of this program, and it's my pleasant duty to thank everybody who has made this program possible. So first and foremost, we would like, so this I'm saying me and my colleague Karam there, we've been the organizers. So we would like to first of all thank the ICTS Programs Committee for approving our program, and for the Department of Atomic Energy, Government of India, for providing the financial support. As for the academic part, we had 10 instructional lectures and 10 research talks. So it's our pleasure to thank Professor Nick Anderson and Professor Michael Griffin, who first of all agreed to visit India despite various challenges, and then came and gave a set of 5 lectures each, which amounted to over 6 hours of teaching. So the depth of understanding and the perspective on harmonic mass forms that they've shared with us has been extremely valuable to us, and all of us have greatly benefited from the lectures that you have given. So thank you so much.